The simulation argument. Imagine that everything you've ever experienced, every memory, every person you've loved, is nothing more than lines of code running on a powerful computer. This isn't science fiction anymore. The simulation argument, formulated by philosopher Nick Bostrom, presents us with three possibilities, and at least one of them must be true. Before we resolve which one it is, make sure to subscribe to our channel to help us make more videos like this. Let's dive in. The first possibility is utterly depressing. Civilizations like ours almost always destroy themselves before they develop the technology to create realistic simulations of their past. We're headed for extinction, and we'll never reach the point where we can build these digital worlds. The second possibility is hardly more comforting. Advanced civilizations that survive long enough to build ancestor simulations simply choose not to. Perhaps they find it morally reprehensible to create conscious beings that can suffer. Perhaps they've transcended to forms of existence so profound that recreating their primitive past holds no interest whatsoever. But the third possibility is where things get truly unsettling. If civilizations do survive, and they do create these simulations, the mathematics becomes terrifyingly clear. A single advanced civilization could run billions or trillions of simulations, each containing billions of conscious minds like yours. The number of simulated beings would dwarf the population of base reality by astronomical proportions. Here's the kicker. If simulated minds vastly outnumber real ones, what are the odds that you're one of the real ones? The statistical probability suggests you're almost certainly living in a simulation right now. Your entire existence might be nothing more than a sophisticated computer program. The observer's paradox. The act of looking changes what you're looking at. This sounds like mystical nonsense, but it's one of the most fundamental and disturbing truths in quantum mechanics. The observer's paradox reveals that reality isn't some fixed, objective thing waiting to be discovered. Instead, it's a participatory process where the very act of measurement helps create the reality being measured. At the quantum level, particles don't exist as definite objects with specific locations and properties. They exist as probability waves, clouds of potential representing all possible states simultaneously. An electron isn't in any particular place. It's in all possible places at once, existing in what physicists call superposition. But the moment you try to measure where that electron is, everything changes. To observe its location, you must interact with it, typically by bouncing light off it. The instant this interaction occurs, the wave function collapses. The cloud of probability vanishes, and the electron is forced to choose a single, definite location. This leads directly to High's simultaneously know both the exact position and Exactenberg's uncertainty principle, which states that you cannot momentum of a particle. It's not because our instruments are imprecise. It's because reality itself has built-in limits to what can be known. The more precisely you measure one property, the more uncertain the other becomes. This creates a profound philosophical problem. What constitutes an observation? Does it require human consciousness, or does any interaction with the environment count? The implications are staggering. If conscious observation is required to collapse wave functions, then consciousness itself might play a fundamental role in creating physical reality. The black hole information paradox. For over 50 years, theoretical physics has been dominated by two extraordinarily successful theories that refuse to play nicely together. General relativity describes gravity and the large-scale structure of the universe with incredible precision. Quantum mechanics governs the bizarre world of atoms and subatomic particles with equal success. But when you try to combine them, contradictions emerge that threaten to break physics itself. The black hole information paradox is where this conflict becomes most apparent. According to general relativity, black holes are cosmic vacuum cleaners with such intense gravity that nothing, not even light, can escape once it crosses the event horizon. Anything that falls in is gone forever, sealed off from the rest of the universe. But quantum mechanics has an unshakable rule. Information cannot be destroyed. The physical state of every particle that makes up any object contains information about its properties, its history, its quantum state. You can scramble this information, transform it, or hide it, but you can never erase it from existence. Here's where the paradox emerges. Stephen Hawking discovered that black holes aren't completely black. They slowly leak radiation due to quantum effects near the event horizon. This Hawking radiation causes black holes to gradually lose mass and eventually evaporate completely over unimaginable spans of time. So what happens to the information that fell into the black hole? If it's destroyed when the black hole evaporates, quantum mechanics is wrong. If it somehow escapes in the Hawking radiation, general relativity's description of black holes as inescapable prisons is wrong. You can't have both theories be correct, yet each has been tested and verified countless times. This isn't just an academic dispute. It's a fundamental crisis in our understanding of reality. The solution might require completely reimagining space, time, and information itself. Some physicists propose that our three-dimensional reality is actually a holographic projection of information stored on a two-dimensional surface. Others suggest that the information is encoded in subtle quantum correlations within the seemingly random Hawking radiation. The stakes couldn't be higher. The resolution of this paradox will likely determine the future of theoretical physics and our understanding of the universe's deepest secrets. It might reveal that everything we think we know about space and time is fundamentally wrong. These paradoxes represent more than intellectual curiosities. They're cracks in the foundation of our scientific understanding, revealing that reality is far stranger and more complex than our everyday experience suggests. Each contradiction points toward missing pieces in our knowledge, gaps that could contain the keys to revolutionary technologies and profound insights about the nature of existence itself. Zeno's motion paradoxes. Movement is impossible. This sounds absurd, but an ancient Greek philosopher named Zeno of Elea constructed a series of logical arguments that seem to prove you can never actually walk across a room. His paradoxes have haunted mathematicians and physicists for over 2,000 years, revealing fundamental problems with how we understand space, time, and infinity. Consider the simple act of walking to your kitchen. According to Zeno's dichotomy paradox, you must first travel half the distance. But before you can cover that remaining half, you must first traverse half of that distance, which is a quarter of the total. And before covering that quarter, you need to cross half of it, an eighth of the original distance. This process continues infinitely. The terrifying implication is clear. To reach your destination, you must complete an infinite number of smaller journeys. You must cross an infinite number of points in space. But how can anyone finish an infinite sequence of tasks in a finite amount of time? It seems logically impossible. Zeno's most famous version involves the warrior Achilles racing a tortoise. Being sportsmanlike, Achilles gives the slower creature a head start. But Zeno argues that the swift warrior can never overtake his opponent. By the time Achilles reaches the tortoise's starting position, the animal has moved slightly ahead. When Achilles covers that new distance, the tortoise has advanced a bit further. This continues forever, with Achilles eternally closing the gap, but never quite catching up. For over 2 millennia, these paradoxes stumped the greatest minds in mathematics and philosophy. The solution finally emerged with the development of calculus, revealing that infinite series can have finite sums. The distances become progressively smaller, and when you add them up, they converge to a specific value. You can indeed complete infinite tasks in finite time, as long as those tasks shrink according to precise mathematical rules. The twin paradox. Time is not the steady, unchanging river we imagine it to be. Einstein's theory of special relativity revealed that time itself can stretch and compress depending on how fast you're moving. This leads to one of the most counterintuitive but experimentally verified phenomena in physics. The twin paradox. Picture identical twins named Sarah and Michael. Sarah remains on Earth, living her normal life. Michael, seeking adventure, climbs aboard an advanced spacecraft capable of traveling at 99% of light speed. He journeys to a distant star system, spends some time exploring, then returns to Earth at the same incredible velocity. When Michael steps out of his ship, he discovers something shocking. While he has aged only a few years during his journey, his sister Sarah has aged several decades. Time moved more slowly for the traveling twin due to a phenomenon called time dilation. Michael has effectively traveled into the future, leaving his twin sister behind in time. But here's where the paradox emerges. From Michael's perspective during the journey, he was stationary inside his spacecraft. It was Earth that appeared to zoom away from him at near light speed, then come racing back. If all motion is relative, shouldn't time have slowed down for Sarah instead? Both twins could claim the other was the one moving, so both should predict the other will be younger. The resolution lies in a crucial asymmetry. Michael experienced massive accelerations during his journey. He had to speed up to near-light velocity, decelerate at the distant star, reverse direction, accelerate back toward Earth, then slow down to land. Sarah, meanwhile, remained in essentially the same reference frame throughout. This acceleration breaks the symmetry and explains why Michael is the one who ages more slowly. The paradox demonstrates that time travel into the future isn't just theoretical speculation. It's a real physical phenomenon that has been measured with atomic clocks on high-speed aircraft and satellites. If you want to see the future, you don't need a time machine. You just need to go really, really fast. Schrödinger's cat. A cat sits in a box, simultaneously alive and dead. This bizarre scenario represents the most famous thought experiment in quantum mechanics, designed to illustrate the strange implications of quantum theory when applied to everyday objects. Erwin Schrödinger created this mental puzzle in 1935 to show how ridiculous he found certain interpretations of quantum mechanics. The setup is diabolically simple. You place a cat inside a sealed box along with a small amount of radioactive material. The quantity is precisely calibrated so that in 1 hour, there's exactly a 50% chance that one atom will decay. Next to the radioactive sample sits a Geiger counter connected to a hammer. If the counter detects radiation from a decaying atom, the hammer smashes a vial of poison, killing the cat. If no decay occurs, the cat remains alive. According to the Copenhagen interpretation of quantum mechanics, the radioactive atom exists in superposition before being observed. It's simultaneously decayed and not decayed, existing in a haze of probability. Since the cat's fate is linked to the atom's state, this implies the cat must also be in superposition. Until someone opens the box to observe the system, the cat is both completely alive and completely dead at the same time. Schrödinger found this conclusion absurd. How can anything be both alive and dead simultaneously? The thought experiment was designed to highlight the ridiculous consequences of applying quantum superposition to macroscopic objects. The act of observation supposedly forces reality to choose, collapsing the wave function and resolving the cat into a definite state. But this raises profound questions about the nature of observation and reality. What constitutes a measurement? Does it require human consciousness, or would a mouse in the box suffice? The many worlds interpretation offers an alternative solution, suggesting that both outcomes occur in parallel universes. When you open the box, you simply discover which branch of reality you happen to inhabit. The paradox continues to challenge our understanding of the quantum world and its relationship to the reality we experience. It forces us to confront the possibility that our everyday intuitions about existence might be fundamentally flawed. The bootstrap paradox. Information appears from nowhere, creating itself in an endless loop with no discernible origin. The bootstrap paradox challenges our fundamental assumptions about causality and creation, presenting scenarios where effects seem to generate their own causes in impossible circular chains. Imagine a passionate music lover who travels back in time to meet his hero, Ludwig van Beethoven. He brings along sheet music for all of Beethoven's greatest compositions. But upon arriving in the 18th century, he discovers that no such composer exists. The man never lived. Horrified at the prospect of a world without Beethoven's symphonies, the time traveler decides to publish the music himself under the name Ludwig van Beethoven. The compositions become famous, inspiring generations of musicians and music lovers, including the very time traveler who brought them back in time. So who actually wrote the music? It wasn't the historical Beethoven, because he never existed. It wasn't the time traveler, because he merely copied existing works. The information seems to have no author, creating itself in a closed causal loop. This paradox becomes even more disturbing when applied to physical objects. Consider an inventor who builds a unique pocket watch, then travels back in time to give it to his younger self. The younger version keeps the watch throughout his life, eventually becoming the old inventor who travels back to give it to himself. The watch is passed along in an eternal loop, never being manufactured, only transferred. But this violates fundamental physical principles. The second law of thermodynamics states that entropy always increases in closed systems. The watch should accumulate wear, scratches, and damage over time. An object existing in an infinite loop should be an infinitely degraded pile of rust and components. The bootstrap paradox suggests that either such causal loops are impossible in our universe or our understanding of information, causality, and physical law is incomplete. Perhaps in the strange logic of time travel, information can exist without an ultimate source, floating freely in the currents of a looped timeline. These paradoxes reveal the deep mysteries that still perplex modern science. Each contradiction exposes limitations in our current understanding, pointing toward revolutionary discoveries that could reshape our comprehension of reality itself. They remind us that despite our technological achievements, the universe still holds secrets that challenge the very foundations of human knowledge. Olber's paradox. Why is the night sky dark? This question sounds almost childishly simple, yet it concealed one of the most profound mysteries in all of astronomy. For centuries, this puzzle tormented scientists and revealed fundamental truths about the very nature of our universe that nobody saw coming. The logic seems airtight at first glance. If the universe is infinite in size, has existed forever, and contains a roughly uniform distribution of stars, then every single direction you look should eventually intersect with the surface of a star. Think of standing in an impossibly vast forest that stretches forever in all directions. No matter where you turn your gaze, your line of sight will eventually hit a tree trunk. If this reasoning holds true for stars, then the entire night sky should blaze with continuous, brilliant light. Every point in the heavens should shine as brightly as our own sun's surface. There should be no patches of darkness, no gentle transition from day to night. The sky should be a searing sheet of stellar radiance that makes twilight indistinguishable from noon. But obviously, this isn't what we observe. We see darkness punctuated by points of light, vast stretches of empty space between distant stars. This contradiction between expectation and reality is Olbers's paradox, named after the 19th century German astronomer Heinrich Olbers, though others had wrestled with this puzzle long before him. The resolution of this paradox provided some of the strongest evidence for our modern understanding of cosmology and the Big Bang theory. The faulty assumption wasn't about star distribution or infinite space. The error lay in assuming the universe is eternal and static. Our universe has a finite age, approximately 13.8 billion years old. This means We can only observe light from stars whose photons have had sufficient time to travel across the cosmic distances and reach Earth. Light from stars that are 20 billion light-years away simply hasn't arrived yet. The observable universe forms a sphere around us, with its boundary defined by how far light has been able to travel since the beginning of time. Even more crucial is the fact that space itself is expanding at an accelerating rate. Edwin Hubble's revolutionary observations in the 1920s revealed that distant galaxies are racing away from us, and the farther they are, the faster they recede. This expansion stretches the wavelengths of light traveling through space, shifting it toward longer, redder frequencies in a phenomenon called cosmological redshift. Light from the most distant objects is stretched so dramatically that it shifts completely out of the visible spectrum into infrared and microwave wavelengths. Their light still reaches us, but it's invisible to our eyes and carries far less energy than it originally possessed. Some objects are receding so rapidly that their light will never reach us at all. The darkness between the stars is actually the ghost of the Big Bang and the shadow of cosmic expansion. It's direct evidence that our universe had a beginning and continues to evolve in ways that would have seemed impossible to earlier generations of astronomers. The Fermi paradox. The universe should be crawling with alien civilizations, yet we're met with deafening silence. This cosmic contradiction has haunted scientists since physicist Enrico Fermi casually asked his colleagues over lunch in 1950, "Where is everybody?" The mathematics seem overwhelming. Our galaxy alone contains between 100 and 400 billion stars. Many of these stellar systems harbor planets, and a significant fraction of those worlds orbit within the habitable zone where liquid water could exist. The universe has been around for nearly 14 billion years, providing ample time for life to emerge, evolve, and develop technology. Even if intelligent life is incredibly rare, the sheer scale of space and time suggests that spacefaring civilizations should have emerged millions of times over. A species just slightly more advanced than humanity replicating probes throughout could send self the galaxy in a few million years, a cosmic eye blink. They should have left traces, signals, massive engineering projects, or at minimum, some form of cosmic debris for us to detect. Instead, we point our most sensitive radio telescopes toward the stars and hear nothing but the random hiss of background radiation. The absence of evidence becomes evidence of absence, creating one of the most troubling mysteries in science. This silence leads to Ailing Possibilities series of Chai, known as great filter scenarios. A great filter represents some evolutionary or technological barrier so difficult to overcome that it prevents virtually all life from reaching an advanced interstellar stage. The terrifying question is whether this filter lies behind us or ahead of us. If the filter is behind us, we might be the universe's first success story. Perhaps the emergence of life itself is so monumentally improbable that it has occurred only once. The transition from simple chemistry to self-replicating organisms might require such an extraordinary confluence of conditions that Earth represents the cosmos's singular achievement. We would be alone not by choice, but by the cruel mathematics of probability. But if the great filter lies ahead of us, the implications are far more ominous. Life might be common throughout the universe, and intelligence might evolve regularly. Yet something consistently prevents civilizations from expanding beyond their homeworlds. Perhaps every species eventually develops technologies that outpace their wisdom, leading to self-destruction through nuclear warfare, ecological collapse, or artificial intelligence that turns against its creators. Alternative explanations offer little comfort. The zoo hypothesis suggests that advanced aliens are deliberately concealing themselves from us, treating Earth like a protected nature preserve. We're cosmic animals in a carefully managed habitat, observed but not contacted. Even more disturbing is the dark forest hypothesis, which proposes that the universe teems with life. But everyone is hiding in terror. Broadcasting your location becomes an invitation for more advanced, more paranoid civilizations to eliminate you as a potential future threat. In this model, the silence isn't emptiness but fear, a galaxy-wide game of deadly hide-and-seek. The grandfather paradox. You build a time machine and journey into the past with noble intentions, perhaps to prevent a historical tragedy or simply to witness a pivotal moment in human history. But through accident, malice, or sheer cosmic irony, you end up causing the death of your own grandfather before he fathers any children. This creates a logical nightmare that threatens to tear apart the very fabric of causality. If your grandfather dies before reproducing, your parent is never born. If your parent doesn't exist, neither do you. But if you were never born, you couldn't have built the time machine that allowed you to travel back and kill your grandfather in the first place. So he lives, reproduces, and eventually you are born, enabling you to build the time machine and travel back to kill him. The cycle repeats infinitely, creating a contradiction that devours its own logical foundations. This paradox strikes at the heart of cause and effect, suggesting that time travel into the past might be fundamentally impossible. Every effect requires a preceding cause, but here the effect seems to eliminate its own causal origin, creating an infinite loop of contradiction. Physicists have proposed several escape routes from this logical trap. The Novikov self-consistency principle suggests that the universe is pathologically determined to maintain causality. You can travel to the past, but you're physically incapable of changing it in ways that create paradoxes. Your weapon will malfunction at the crucial moment. You'll slip on an improbably placed obstacle. You'll experience a sudden change of heart that prevents you from completing the deed. The laws of physics would conspire in increasingly absurd ways to preserve the timeline's integrity. A more intriguing solution involves the many worlds interpretation of quantum mechanics. When you travel back and alter the past, you don't destroy your original timeline. Instead, you create a new branch of reality, a parallel universe where your grandfather dies and you are never born. You become a temporal refugee, stranded in an alternate history that you've created but can never call home. This resolves the paradox by allowing both outcomes to coexist in separate realities. Your original timeline continues to exist, ensuring your birth and enabling your time travel. The alternate timeline you create represents a different possibility, equally real, but forever separated from your point of origin. Both solutions carry profound implications for free will, determinism, and the nature of reality itself. Either we live in a universe where the past is absolutely fixed and unchangeable, or we inhabit one of countless parallel realities branching endlessly through space and time. These paradoxes don't just challenge our understanding of specific physical phenomena. They reveal fundamental gaps in our comprehension of reality's deepest structures. Each contradiction points toward missing pieces in the grand puzzle of existence, gaps that might contain the keys to revolutionary breakthroughs in physics, technology, and our understanding of consciousness itself. The resolution of these paradoxes will likely require us to abandon some of our most cherished assumptions about the nature of space, time, information, and causality. We may discover that reality is far stranger, far more complex, and far more malleable than our everyday experience suggests. What we consider solid, objective truth might be nothing more than useful approximations that break down when pushed to their logical extremes. But perhaps most unsettling of all, these paradoxes suggest that the act of asking questions about reality might itself change the nature of that reality. We are not passive observers of an independent universe. We are active participants in an ongoing creation where consciousness, measurement, and knowledge play fundamental roles in determining what exists and how it behaves. The journey through these mind-bending paradoxes reveals something profound about the nature of scientific inquiry itself. We've explored contradictions that challenge our most basic assumptions about time, space, causality, and existence. But there's one final realization that emerges from this exploration, something that might be the most unsettling discovery of all: the nature of scientific truth. These paradoxes aren't just intellectual curiosities or mathematical puzzles waiting to be solved. They represent fundamental cracks in the foundation of human knowledge, revealing that our understanding of reality is far more fragile and provisional than we typically admit. Each contradiction we've examined exposes the limitations of our current scientific frameworks and suggests that revolutionary discoveries await us in the gaps between established theories. Consider how many of these paradoxes arise from the collision between different levels of description. The grandfather paradox emerges when we try to apply classical logic to time travel. Schrödinger's cat appears when quantum mechanics meets macroscopic objects. The black hole information paradox erupts from the conflict between general relativity and quantum theory. These aren't failures of science, they're growing pains that signal we're approaching the boundaries of our current understanding. What makes this especially remarkable is how these paradoxes often point towards solutions that seemed impossible or absurd when first proposed. The idea of parallel universes emerging from quantum mechanics was once considered fringe speculation. Now it's a serious contender for resolving multiple paradoxes simultaneously. The notion that space and time are emergent properties rather than fundamental features of reality was once unthinkable. Today, it's at the forefront of theoretical physics research. The recursive nature of knowledge. Perhaps the most profound insight emerging from these paradoxes is that knowledge itself might be recursive and self-modifying. The observer's paradox suggests that the act of gaining knowledge changes the system being studied. The simulation argument implies that our very existence might depend on the computational processes of minds seeking to understand their own origins. The bootstrap paradox shows how information can exist without an ultimate source, creating itself in closed loops of causality. This points toward a startling possibility. Maybe consciousness and knowledge aren't separate from physical reality, but are fundamental components of how reality constructs itself. The universe might not be a vast machine that we observe from the outside, but a participatory process where observation, measurement, and understanding play active roles in determining what exists and how it behaves. The price of understanding. These 10 paradoxes reveal that reality is far stranger than our everyday experience suggests. From time travel contradictions that devour their own logic to quantum mysteries that make consciousness a fundamental force. Each paradox exposes cracks in our understanding of existence itself. They're not just intellectual puzzles. They're roadmaps to revolutionary discoveries that could reshape physics, technology, and our comprehension of what it means to be conscious observers in a participatory universe. The most unsettling truth might be that the act of seeking answers changes the very nature of the questions we're asking. Reality, it seems, is not a fixed stage we observe, but an ongoing collaboration between mind and cosmos that we're only beginning to understand. You know it as you made it this far. To help us publish more videos like this, please consider to subscribe to our channel